When we listen to health experts, we're told that saturated fat is poison. So if that were true, are our bodies trying to kill us by storing that very poison, that saturated fat? If that were true, we would not exist. For millions of years, organisms have been storing saturated fat in order to survive times of food scarcity. So let's look at fat, one of the other macronutrients. Please like and subscribe to this video. The three macronutrients are carbohydrates, fats, and protein. So fats consist of carbon, hydrogen, and oxygen, which makes them a hydrocarbon. Fat is basically just a long string of carbons. And on the top and bottom, if you're looking at them, is a hydrogen atom. You can sort of consider carbon as having four free hands. They have four unpaired valence electrons. And hydrogen has one free hand. So in a fat molecule, the carbons are holding on to each other with their free hands on both sides. And at the top and the bottom, the carbon is holding on to hydrogen atoms. And that string is a fatty acid. Now, there are characteristics of these fatty acids that we probably have heard of before: saturated and unsaturated. So saturated simply means that all of the carbons are holding on to two hydrogens and each other. When they're unsaturated, there are some hydrogens missing, and the carbons have to hang on with those free hands with two hands to each side of them. And so you can see that from this diagram. So a saturated fat then, because all of the bonds are used up with either a carbon to each side or a hydrogen, it is considered saturated. All of the available bonds to that carbon are taken up, and specifically, they are taken up by hydrogens. So, an unsaturated fat occurs when two of those hydrogens are missing. Now, in a saturated fat at room temperature, these long chains of fat can easily pack on top of each other. And at room temperature then, those saturated fats, those long-chained saturated fats, we'll get into that, are easily packed and they become solid at room temperature. Unsaturated fats, on the other hand, have a kink. And because of that kink, they cannot pack very well, so they remain liquid. So oils are unsaturated fats. And there are two kinds of unsaturation. There's cis unsaturated fats and trans unsaturated fats. The difference is that the cis unsaturated fat is missing hydrogens from either the top or the bottom, which causes a kink because the remaining hydrogens repel each other and cause a little kink in that molecule. The trans unsaturated fats are missing a hydrogen on the top and on the bottom, so that there is no repelling going on between hydrogen atoms, and so that molecule remains straight. And you've probably heard of trans fats and how they affect our health. They are very unhealthy. And examples of trans unsaturated fats are things like Crisco and margarine. Now, examples of saturated fats are butter, coconut oil, lard, ghee, tallow, that sort of thing. Examples of unsaturated fats, cis unsaturated fats, are cold-pressed olive oil and avocado oil, and then also polyunsaturated, high-heat, and chemically treated harmful seed oils like canola oil, cotton, sunflower, safflower, corn oil, all those things that are processed with incredibly high heat and chemical solvents like benzene. So all of these seed oils that we use to cook our foods with those are the poisons. And in fact, polyunsaturated fats, like I just mentioned, cottonseed, corn, canola, sunflower, safflower, those seed oils were originally intended to be used as machine lubricants. But later on, food companies took those oils and thought, hey, let's feed these to human beings. So they used all these processes, a highly processed product. So it removed the odors and the tastes and the color from these things because those were meant for machines not to be eaten. And they processed these things so incredibly so that it would become something that humans would actually look at and be able to smell, and they wouldn't run in horror. And those are what we're putting into our bodies. And those are causing a lot of health issues. I could go on forever about that, but a lot of people have already done that, and I'll put some links in the show notes to show more about that. So let's talk now about fatty acids. There are a couple different forms of fat. There's a fatty acid or a triglyceride. Let's consider those two types. A fatty acid is basically what we just looked at. It's a long string of carbon atoms strung together, and on one side there is a carboxyl group, and on the other side is just a hydrogen that just sort of terminates that molecule. Now, there are different lengths of fatty acids. There are short-chain fatty acids, medium-chain fatty acids, long-chain fatty acids, and some very long-chain fatty acids. Very long-chain fatty acids are things like waxes. So let's talk about the short-chain fatty acids first. The main types of short-chain fatty acids are acetate, propionate, and butyrate. Those short-chain fatty acids range in the number of carbons from 2 to 4. And those short-chain fatty acids are created either in our gut through fermentation, or they can be found in fermented things like vinegar. Vinegar is acetic acid, which is something that I found very fascinating. Vinegar is actually a fat. Short-chain fatty acids. Other short-chain fatty acids are formed in other fermented foods like yogurt and kefir. The short-chain fatty acid acetate is also derived from alcohol. But when we drink alcohol, it goes through a couple of different processes before it gets to acetate. First, alcohol dehydrogenase strips a couple of hydrogen from the alcohol molecule and creates a group 1 carcinogen called acetaldehyde. Acetaldehyde is incredibly dangerous. It causes all the drunk feelings we get. It affects our brains. It makes us flush. And it sticks around in our bodies at various lengths of time depending on whether or not you have the next enzyme that's required. And that is aldehyde dehydrogenase, which strips some more hydrogens off of the acetaldehyde to create acetate. And that acetate then is used as an energy source. So alcohol actually does generate some sort of energy for us in the form of acetate, but it's only after we are exposed to a group 1 carcinogen. Short-chain fatty acids have a number of beneficial effects. They can be used as energy right away. They're small enough that they can actually travel in our bloodstreams, unlike other fatty acids. They can strengthen the gut barrier. They create a protective environment in our guts by lowering pH, making it more acidic, so the bad bacteria are killed off. They help with our appetite and our satiety. They naturally promote GLP-1, glucagon-like peptide 1, which is basically what a lot of the GLP-1 agonists do that we inject into our bodies for thousands of dollars a month. That people are led to believe that these are the best ways to lose weight, when actually, when you start injecting these GLP-1 agonists like Wegovy, you end up losing not only fat mass, but also muscle mass. And so that's another horrible trail that pharmaceuticals are sending us down, believing that pharmaceuticals will save us from everything. But there are always side effects to pharmaceuticals. The next type of fatty acid length is the medium chain fatty acids. Those can range from 6 to 12 carbons in length. And those are caproic, caprylic, capric, and lauric acid. These acids, these fatty acids, are used for energy. They're easily broken up, and they're used by the liver to create ketones. And ketones are just another energy source that can be sent through the whole process to create ATP. You may have heard of medium chain triglycerides, MCT oils. Now, these MCT oils are made from usually coconut oil, and they can help your body to become more fat adapted because they're used immediately by the liver to create energy. Neither short nor medium chain fatty acids can be stored in our bodies as adipose tissue or fat. Both short and medium chain fatty acids must be used as energy or some other purpose. They cannot be stored in our bodies. So that's kind of an interesting fact. If you take a teaspoon or two of MCT oil in your coffee in the morning, there's no worry that that's going to be stored as fat, because either it's going to be used for energy or it's going to be eliminated from the body. Now, long-chain fatty acids are where the rubber really kind of meets the road. They're used for so many things in our bodies. So they can help to create energy when they're broken up through something called beta oxidation. They're structural components in all of our cell membranes. They're signaling molecules to regulate immune and metabolic functions. And unlike short and medium chain fatty acids, long chain fatty acids, when they're packaged up as triglycerides, are what our body stores for energy, for survival. And that's where the whole story of saturated fat kind of falls apart. Because if we have too much energy in our bodies, either coming from fructose or glucose, that energy is then converted into fat. That glucose, that extra glucose that is not being used for energy at the time, is actually converted into saturated fat and sent to our fat cells for storage. Our body actually takes carbohydrates and makes fat out of it and stores it for our survival. So saturated fat, if it were so bad, why would our bodies actually create it and store it for our survival? Because millions of years have passed with us storing saturated fat, and we've been surviving just fine. Until the last 80 to 100 years or so, or maybe less, when these polyunsaturated fats started coming into our lives. And we were told that these polyunsaturated fats will keep us from dying from heart attacks. But prior to 1800, it was very, very rare for people to get cancer or die of heart attacks. Now, heart attack and cancer are the top leading killers in the United States and across the world. And in fact, when our body creates those saturated fats from carbohydrates, that is considered de novo lipogenesis, creation of fat from new. And the types of fat that our bodies store are palmitic acid, which is 16 carbons long, stearic acid, which is 18 carbons long, And it also can use those as a substrate to create a monounsaturated fat called oleic acid, which is the same thing that you find in olive oil. Oleic acid is also stored in our bodies to sort of help lubricate things. During fasting and exercise, especially zone 2 exercise, long-chain fatty acids are used for energy. They're broken up, cut at the second carbon, the beta carbon, and oxidized. So it's called beta oxidation. So those long-chain fatty acids are taken and broken up and sent through the energy process to create ATP for us. Long-chain fatty acids are also what make up phospholipids. Phospholipids are basically these little molecules of fat and a phosphate group that we'll talk about very soon that make up our cell walls. So let's get to the structure of cell walls and how those phospholipids are formed. So a phospholipid has a phosphate group, and off the bottom of that phosphate group are two fatty acids. And in particular, they are long-chain fatty acids. When a bunch of these phospholipids get together in a liquid, they start to migrate together and start to pack, and they form a long chain of phospholipids. And that can sometimes turn on itself and be enclosed in kind of a bubble. And those little bubbles are called micelles, M-I-C-E-L-L-E. Those micelles are used to transport things, especially like in our small intestines. After emulsification of fats has occurred in our small intestines, those micelles then take the fats, the triglycerides, and at that point, the fatty acids and the monoglycerides to our stomach lining and pass it off to our stomach lining cells. Those phospholipids can also form a double layer with a phosphate group, the fatty acids, and then on the bottom, the phosphate group and the fatty acids. So they're pointing at each other with the fatty acids. That creates a really amazing little structure. So the phospholipid on the blue phosphate group side is water soluble, hydrophilic, and the fat side, of course, is hydrophobic. It likes fat but not water. So if something tries to get through this phospholipid bilayer, it first encounters the water soluble portion, and if it's water soluble, it passes right through that. But once it gets to the inner portion where the fatty acids are, it is no longer able to pass through that because it's not fat soluble. So just in that, the phospholipid bilayer is really an incredible way to keep things out or keep things in if they're already in the cell. So these phospholipid bilayers are actually what create the membrane around our cells. There are other things on the cell membrane, such as cholesterol and proteins. Now, the proteins are usually used as some sort of shuttle, some sort of transport to allow certain things in and into and out of the cell. So they're very important. Another way that polyunsaturated fats are not very good is that if we eat polyunsaturated fats, when we ingest them, they are used to help create the structure of our cells. But because they are liquid and they don't pack very tightly, these polyunsaturated fats can actually make our cells more permeable than they should be. So things can get in and out of the cell that shouldn't be able to transport just that easily. But with polyunsaturated fats encompassing the structure of that phospholipid bilayer, that cell then becomes much more permeable and much less healthy. All right, so we've talked a little about triglycerides. Now, triglycerides are sort of like a phospholipid, but instead of a phosphate group, it's a glycerol backbone, they call it. That glycerol backbone then has 3 fatty acids hanging off of it, making a triglyceride. Now, those triglycerides are what our bodies store as fat, and it's usually the kind of fat that we find in our food. And as we discussed in the carbohydrate episode, and also here, if we take in a large number of carbohydrates, a large amount of glucose, that extra energy is turned into fat, and it is the type of fat that triglycerides are. And those triglycerides then are created by the liver and sent out to the body to be stored. Measuring triglycerides in your blood, if you have high triglycerides and low HDL, if that ratio is less than 1, you're in good shape. But if it's over 2, then that's a really bad sign, and there should be something done about that. That ratio, triglycerides to HDL, and just the number of triglycerides in your bloodstream, is much more important of a marker to show either health or a transition to unhealth than LDL. LDL is very nuanced, and LDL has actually been found in numerous studies to decrease all-cause mortality in older adults, because older adults have an immune system that starts to be less effective. LDL has on its exterior receptors that gather up lipopolysaccharides. Lipopolysaccharides are parts of bacteria that can contribute to upper respiratory diseases and other things like sepsis. And so people who have higher levels of LDL, adults with higher levels of LDL, have a much lower all-cause mortality than those with lower LDL. In fact, it's kind of a bell curve. Those at the low end of the LDL curve, which would be low LDL, are just as likely as those with very high LDL to have all-cause mortalities that are higher. Those with 130 as their score are the most healthy. And so I have 130, and I've been told since I was at 100 that I should be on statins. All right, so let's take a really quick journey of fat from our mouths to our bloodstreams or our liver. So first of all, we take a bite of something with fat in it. Instantly, while we're chewing that up, there's an enzyme called lingual lipase that starts breaking that down. Then we swallow that through our esophagus. It gets down to our stomachs through the lower esophageal sphincter. And the gastric lipases start working on it, breaking it up some more. And as that breaks up, it kind of forms these little bubbles of fat. Then when it dumps through the pyloric sphincter at the bottom of the stomach into the small intestine, the duodenum, there are a couple of things that are released that start to help break that up. There's something called secretin that helps to release bicarbonate in the small intestine to increase the pH, to reduce the acidity of that chyme which comes out of the stomach. Now, as that pH starts to increase and the acidity goes down, that makes it more available for some other things to occur. And that's when cholecystokinin is released, and that cholecystokinin, or CCK, makes the gallbladder constrict. And when that gallbladder constricts, it forces out a bunch of bile salts. Now, after all this is going on and all those lipases are breaking this fat down, that fat needs to be emulsified so it'll break up even more. And that's what the bile salts do, is that it sort of emulsifies. It allows, sort of like if you were to stick oil into water, an emulsifier might be some dish detergent. You put that in there, and now this fat starts to break up, and it becomes easier to clean your dishes. So in our small intestine, that same emulsification is occurring. And now is when something really amazing happens. The pancreas, based on this high acid stuff that has just come into the duodenum, that high acid stuff from your stomach, the chyme, actually triggers a whole bunch of things. It, of course, the secretin brings down the acidity. The cholecystokinin helps bring in the bile salts, but then the pancreas starts to release pancreatic lipase, which is very amazing stuff. It starts to actually look at those triglycerides, and it starts breaking fatty acids off one by one until you end up with just a monoglyceride and 2 fatty acids. And that's where these little micelles that we talked about earlier with the phospholipid single layer start to encapsulate those single fatty acids and those monoglycerides. And they bring those to the sides of the small intestine where there are cells called enterocytes. And those enterocytes then absorb those fats, and then the micelles are free to go off and do whatever they do after that. So once it's inside of that cell, those monoglycerides and those fatty acids are then reconstructed into triglycerides. And those repackaged triglycerides then are stuck into a large bus that's called a chylomicron. So this chylomicron gets filled with cholesterol that was in the food, these triglycerides, fat-soluble vitamins, and then they're sent out of the enterocyte into our lymph system. And it goes from the thoracic duct of the lymph system into the bloodstream. Now, the reason it has to do this is because these chylomicrons are too large to fit through our capillaries, like through our fingers, these little capillaries. So it has to be sent to a part of our bloodstream that doesn't have to worry about size. So that's where those chylomicrons then are sent through our thoracic duct of our lymph system, then to our bloodstream, and then from there it can actually go to the liver, where it's torn apart. The chylomicrons are then, all the cargo that was in the chylomicron is then taken and repackaged into something called VLDL, very low density lipoprotein, and that's sent again out of the liver, and that can be brought to cells that need to be repaired. So all these things that are within this VLDL are then used by cells to fix themselves or to store more fat. As that VLDL is giving up its cargo, it goes through a couple of steps. It becomes an intermediate density lipoprotein, IDL, and then finally an LDL, low density lipoprotein. Those are all of the steps it takes just to get to an LDL or to get into our liver, which is kind of interesting because I think there's a notion that if we eat saturated fat, that saturated fat will stick to the inside of our arteries and cause plaque. Well, saturated fat never ever is in our bloodstreams. And if it is, there's something else wrong, and that person is very sick. Saturated fats entirely, are always within these little buses, either a chylomicron, a very low density lipoprotein, an intermediate density lipoprotein, or a low density lipoprotein, or an HDL. LDL is not cholesterol. It's neither good nor bad. It simply is a carrier of things. There's a protein on the outside of the LDL. That's why it's called a low density lipoprotein. There's a protein on the outside that can have some role in how it is used in the bloodstream. As far as plaque goes, I can go into a whole bunch of things because there's so much to say about fat and lipoproteins and things. But when there's damage done to our arteries, that's when the repair of that damaged section happens, and that's where a bunch of things come in to fix that damage. And that's the process whereby some plaque can be created. What's interesting is there never is any plaque in a vein. It's always arteries. And so even if you had high LDL and your doctor's telling you it's horrible, it's interesting that we don't end up with plaque in our veins, but only in our arteries. And the main reason for that is the high pressure that's in arteries. There's also kind of another little thing with glucose. If our glucose levels are always high, our serum glucoses are always levels are always high, there are these little fibers on the inside of our endothelium, the cells that make up the cell walls of the arteries and veins. Now these cells are protected by these little fibers called glycocalyx. And glycocalyx just makes that interior space a lot more slippery. It's sort of like a fish is slippery. When we eat a lot of glucose, a lot of carbohydrates, and we have high serum glucose, that glucose sort of clogs up those glycocalyx, and they kind of die off, and they break off in our bloodstream. And you can actually take a blood test and see that these things are breaking off and they're floating around in our bloodstreams. When that breaks off, it exposes part of our artery lining, that endothelium. And the things that are rushing by, especially in a high pressure situation like an artery, starts to damage that surface. And when that surface is damaged, it can start to bleed and it can scab over. And when it causes a scab, that results in kind of a clot. And the clot is the dangerous part. So instantly our bodies start working on that clot. They want to make sure that clot does not get away. So all sorts of things like macrophages and even LDL come and try to cover that up. Meanwhile, there are some cells that are called endothelial progenitor cells that come to the rescue, and they start covering up that clot. And as it covers up, soon another layer of endothelium is on top of that clot, and it forms a little hump. If no more damage occurs on that very same space, then that clot can maybe be reabsorbed, and we won't even know that it was there after a period of time. But what happens in some cases is that there's damage and more damage and more damage, so it never really is able to heal and be reabsorbed. So that clot starts to change and become larger. And if that becomes too large, it starts blocking off the artery. And that's where the problem comes in. So that's kind of a simplistic mechanism for how clots form in our arteries. All right, so like I said, fats are so incredibly complex and so important to life itself. This could be a really long episode, but I think I need to just sort of stop here. So in review, fats are either fatty acids or triglycerides that we've talked about. Fatty acids are found in different lengths. There's short, medium, long, and very long. The very longs I didn't really go into, but those are things like earwax and candle wax and things like that. Short and medium chain fatty acids cannot be stored as energy. They can only be used to create energy. They can only be used as fuels. So we cannot store those fats on our bodies. Things like vinegar and MCT oil, medium chain triglyceride oil from coconut oil. Fats can be saturated, like the kind we store on our bodies, or they can be unsaturated, monounsaturated, like oleic acid, like olive oil, and avocado oils, which are actually pretty good because when they make olive oil and avocado oil, they cold press them. They just simply take the fruit and squish the poop out of it, well, or the oil out of it, and that's what we get. So extra virgin olive oil and avocado oil are actually okay because they haven't been damaged. They haven't been processed with high heat and chemicals like polyunsaturated fats that we find in our cooking oil, that is seed oil consisting of canola, sunflower, safflower, corn, all those horrible things. Cottonseed is actually the worst because cotton is not considered a food crop. So they can use all sorts of chemicals on the plant, and then they can use those seeds to add to food. And that those seeds are not only been processed and destroyed that way, they're all full of all sorts of chemicals. So just stay away from cottonseed especially, but all the rest of them too. Eek. Okay, so especially saturated fat is vitally important for our survival. It's used as storage in case of food scarcity. It becomes part of our cell membranes. It's a signaling molecule for various processes. And if saturated fat was going to kill us, then our bodies would not store it. So I guess that's my main message here, is that if our bodies were storing saturated fat for our very survival, then if it were going to be killing us, we wouldn't survive millions of years of evolution. But we have. So that, for me, proves that saturated fat is not the bad actor here. All right. Well, thank you for listening, and please like and subscribe, and I'll see you next time.